In security architecture, cryptography functions as a continuous structural arms race between engineers building mathematical walls and adversaries building the tools to break them. The core operational challenge is protecting sensitive information across three vulnerable states: data at rest on a storage drive, data in transit traveling across a network, and data in use existing actively in system memory. This foundation is built on four specific pillars. Confidentiality ensures data remains private. Integrity guarantees data is not altered. Authentication verifies a user's claimed identity. And non-repudiation provides assurance that a sender cannot deny originating a message. These goals are not always pursued simultaneously. Rather, crypto systems are specific tools applied to mitigate particular vulnerabilities. Effective security requires selecting the exact mathematical tool to enforce a required state, moving past the simplified notion of universal encryption. There is an intuitive assumption that keeping the inner workings of an algorithm secret provides a layer of protection against attackers. Modern engineering rejects this, operating instead on Kirchhoff's principle, the assumption that the system remains secure even if the enemy knows exactly how it works. Trust is placed in the secrecy of the key rather than the secrecy of the mechanics. This allows the algorithm to be publicly peer-reviewed and tested for weaknesses. This strength is derived from the key space, which is the range of values valid for use as a key in a specific algorithm. In a 128-bit key space, there are 2 to the 128th power possible combinations, a number so large that it renders brute force guessing mathematically unfeasible. Relying on public, battle-tested algorithms paired with massive key spaces provides a level of verification that secret, proprietary code cannot match. At the hardware level, computers only process binary, on and off electrical states, which we interpret as true and false. Boolean logic serves as the mathematical nervous system of these circuits, utilizing logical operations like and, or, and not to manipulate data bits. The exclusive OR function, or XOR, only returns a true value of 1 when exactly one input is true. Here, plain text string X is combined with key string Y. Applying XOR bit by bit transforms the data into a unique ciphertext. XOR is utilized throughout cryptography because it efficiently scrambles data at the binary level. The operation is reversible. Applying the exact same key to the ciphertext perfectly retrieves the original plaintext message. However, XOR alone is vulnerable if the underlying data contains predictable patterns, or if the same key is reused for multiple communications. While XOR provides a reversible lock, it requires additional mathematical layers to prevent adversaries from identifying structural patterns in the scramble. This leads to the modulo function, or mod, the remainder value left after a division operation. This keeps calculations within a computer's finite memory. Modular math traps numbers within a repeating loop, ensuring data stays within predictable hardware limits. XOR handles the scrambling, while modulo arithmetic ensures the resulting ciphertext remains within fixed, manageable bounds. Enforcing integrity and non-repudiation requires mathematical operations that are easy to compute forward, but practically impossible to calculate backward. We achieve this with one-way functions. Multiplying 3 5-digit prime numbers instantly produces a 14-digit product. But the reverse, factoring that product back into its original primes, requires checking thousands of combinations, a task that grows exponentially more difficult. Even with strong math, predictability remains a risk. Encrypting identical plaintext twice with the same key produces identical ciphertext, offering a structural clue to attackers. Engineers solve this by injecting a nonce, a number used once, often as an initialization vector. This random bit string is XORed with the message to ensure that every encryption cycle produces a unique ciphertext. One-way functions target the mathematical feasibility of working backward, while nonces actively mitigate the risk of pattern recognition. These layered constraints force an adversary to attack both the algorithm's structure and its inherent randomness. Authentication requires a user to definitively prove they possess a secret without exposing that secret to a third party. This is achieved through a zero-knowledge proof, a mathematical mechanism that allows for the verification of a fact without disclosing the fact itself. Consider Peggy and Victor at a circular cave, where a locked door separates path 1 from 2. Victor watches Peggy enter path 1 and emerge from path 2. By returning via the opposite path, she proves she knows the password without Victor seeing it. We must also account for human risk. Techniques like split knowledge and key escrow ensure that no single person, such as a rogue administrator, can unilaterally decrypt sensitive information. This is managed through M of n control, where a master key is divided into a total number of parts, n. A specific minimum threshold of parts, m, must then be combined to reassemble the key for use. These architectural safeguards ensure that proving an identity or storing backup keys does not inadvertently create a single point of failure within the system. At the macro level, we must determine a standard to measure if a crypto system is truly secure. This is the work function, or work factor. It represents the total effort, time, and computational cost required to successfully execute a brute force attack against an encryption system. In cryptographic engineering, security is strictly an economic equation. A system is considered successful if the work function required to break it outlasts the total time value of the protected asset. If information loses its value over time, the protection only needs to hold until that value is gone. All cryptography must be proportional and cost-efficient. The work function equation is dynamic. It shifts as adversary technology improves. Advancements in cloud-based parallel computing and quantum computing are steadily lowering the computational cost and time required for brute force attempts. Regardless of the hardware, the objective remains the enforcement of confidentiality, integrity, authentication, and non-repudiation. Quantum threats will eventually require exponentially larger key spaces and new post-quantum algorithms, but our primary defense will continue to be the mathematical difficulty of the challenge. The security of a system is a result of rigorous, continuous mathematical constraints designed to ensure that breaking the rules is simply too expensive for the adversary to afford.